Hey class, in today's lesson we're going to talk about exploring exponential models, which is found in section 7-1, part 2 of your book. Our objective is going to be to model exponential growth and decay. Alright, so with exponential growth, it says for exponential growth, the formula below, which is y equals a times b to the x, we've used before, where b is greater than 1, then the value of b is the growth factor. A quantity exhibits exponential growth increases by a constant percentage each time period. The percentage r, written as a decimal, is the rate of increase or growth rate. And to find exponential growth, we use b equals 1 plus r. So now, in this go round, really, we can also see this rewritten as y equals a times 1 plus r to the x. So we may not always know what b is, but if we know what the rate is, we can go back and find what the growth rate is, or the b. Alright, so exponential decay, it says for exponential decay, b is less than 0 but greater than 1, and as a decay factor, the quantity decreases by a constant percentage each time period. The percentage decrease r is the rate of decay for exponential decay. B, which is 1 plus r, r is now going to be a negative quantity. So again, we would use that same formula, y equals a times 1 plus r to the x. And the last one, when it was growth, r was positive. And it's decay when negative. Okay? All right, let's keep going. All right, so now we have a different formula. Not really, but we do. It says, so A of t, which is the amount of years after a certain time period, equals A, the initial amount. So we should know that because this is also our y-intercept, right? Times 1 plus r, but remember this 1 plus r is really b, but they're telling you that when r is greater than 0, it's growth, and when it's less than 0, it's decay. And then t, of course, is the number of time periods. And the main thing that you need to be sure that you understand is that this is fixed percentages. This is fixed percentages. All right, let's keep going. All right, so in example 3, now we're going to start modeling. It says you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So here we go. So let's identify A first. A is the initial investment, or the initial amount, which we know is going to be $1,000. This is also our y-intercept, right? R is our rate, but it needs to be in decimal form. So though it's 5%, as a decimal is 0.05. And lastly, t is time, and t is going to be 6 years. Okay, so then if we throw this into our formula, A of 6, right, is going to equal A, which is 1,000, times 1 plus 0.05 to the 6th power, which is really 1,000 times 1.05 to the 6th power. If you do order of operations and do 1.05 to the 6th power first, and then multiply that times 1,000, you'll get $1,340.10. Okay, let's try the next one. So suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? So again, A is going to be $500. R, your rate, is 3.5%. However, we need to change it to a decimal, which is 0.035. And T is going to be 5 years. So A of 5 is going to be 500 times 1 plus 0.035 to the 5th power. Okay, if you multiply that out using order of operations, you should get $593.84. So the things that really affect your overall outcome, the main things are obviously a higher rate and higher time, and also a higher initial input. But obviously, the main thing that most people normally are able to control, you normally can't control the rate, so that's not something that we can ever really kind of control. But you can control whether putting something in there for a certain amount of time or increasing that initial amount. So anyways, that was just a investment background piece. All right, a little bit more vocabulary. So it says to model a discrete situation using an exponential function of the form below, which is again that y equals a times b to the x, you need to find the growth or decay factor b. So if you know the y values for two consecutive x values, you can actually go back and find r, which will then help you find b. Okay, so that's what we're going to be faced with on our next problem. We will know, we may be able to find a pretty easily, but we may not be able to find b so easily, but we can find r if we can use two consecutive y values, or two y values that are from two consecutive x values. So let's take a look at that. It says the table shows the world population of the Iberian lynx in 2003 and 2004. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will be there in 2014? Now, two things stood out to me. First of all, I noticed a 2003 and a 2004. So those are consecutive. Those are going to be my consecutive x values, which are found in this table. So if that's going to be x1 and x2, then this must be y1 and y2. Also, the other thing that helps me understand this problem is that they say it is decreasing. So this should be decay in the end. If my r does not reflect something that is of decay, then I've probably done something wrong. Okay. All right, so moving past that, we need to go ahead and determine what that r value is going to be. So again, r is y2 minus y1 over y1. So y2 is 120 minus 150 over 150. That's really negative 30 over 150. Reduce that and you get negative 0.2. So to find b, remember b equals 1 plus r. And if r is negative 0.2, then we know that b is 0.8. Now that helps us with our overall formula. Now remember, the formula is supposed to be y equals a times b to the x power. B now is 0.8. Y is actually going to be our initial y, our y1, so that's 150. So this is really 150 a times, 150 equals a times 0.8 to the x power. Okay, now moving from there, to be able to determine what a is, remember, because that's our y-intercept. Actually, I didn't even need to do this. Let me go back a step. We should know that our y-intercept is always our initial y value, right? So our y-intercept here is 150, but to prove that to you, I actually will go back and write that. This is 150 because that's the first y, equals a times b is 0.8. And to figure out what the y-intercept is, remember that's when x is 0, so you substitute in 0 for x. Obviously 0.8 to the 0 power is 1, so then you would get that a is equal to 150, which was basically just proving what I said anyway, that since we know that a is a y-intercept, just look back at the first y value. Okay, so now I'm going to rewrite this in the correct form and get rid of this work. And just write y equals 150 times 0.8 to the x power. Now, to be able to determine how many links there would be in 2014, you need to take that year and subtract it from the first year we're given. So 2014 minus 2003 we know is 11 years. So to figure out what that is, we will have 150 times 0.8 to the 11th power. If you type all of that into your calculator, you're going to get about 13 Iberian links left, if it stays at that same constant rate of about an 0.8, or actually a decrease of 20%. All right, so that is it for that problem. We're going to expand this just a little bit by going to the try. So let's look at the try. It says, for the model in problem 4, what will be the world population of the Iberian lynx in 2020? So we're really not switching up much. Again, we're going to keep the same formula. Y equals 150 times 0.8 to the x power. Now it's 2020 is the year, so 2020 minus, that's a 0, minus 2003. We should know that that's a 17-year difference. So if I substitute 17 for my x, we should get an answer of about 3 Iberian lynx. And that is it, guys. Remember, if you have any questions or if you need to come in for additional help, please come see me for tutoring.